Okay, so welcome to Module 13. We discussed computational complexity, which is a formalization of order of growth. And then we saw how to compare and contrast different algorithms with, well, if they have quite different computational complexity, you choose the lower one, the faster one. And if it's comparable, at times you need to look at the details. And now we're going to see how to use that to design algorithms. So a typical approach is called divide and conquer. You have an algorithm that you can partition it into parts. The divide part means that you're taking the algorithm and you're partitioning it into subproblems. And then we'll have some number of subproblems, and we'll conquer each of them recursively. So for example, recall that we had a sorting problem, and in merge sort, a problem of size 8, ms of size 8, we partitioned it into two problems of merge sort of size 4, ms of 4, and another ms of 4. And we conquer them recursively. So once we provide a function call to merge sort of 4 for the first part, merge sort of 4 for the second part, maybe it'll continue running recursively, maybe not, maybe it'll be a basis case. And after that, we combine the solutions with the merge routine. And if the problem is small enough, we solve it directly, else we apply the recursion to subproblems, but only if it's big enough. We saw the merge sort example. Another example is the fast Fourier transform, and so on. So what's the running time? The direct solution of a small problem is theta of 1. Theta of 1 means basically constant. And what's the solution for the general case? So dividing a problem of size n into a subproblems of size n over b takes d of n time. Now recall, a subproblems of size n over b, and you may think, oh, a and b should be identical, but that's not necessarily the case. So imagine that b is equal to 3, meaning that we're partitioning the larger problem into chunks of size 1/3, but what if they overlap? So this would be the first one of size 1/3, the second one, the third one, the fourth one, the fifth one. B equals 3, but A equals 5. And we can see that A could be equal to B, but it could also be larger. So dividing takes D of n, combining takes C of n, and running A problems each of size n over B, if we denote the resource consumption, the computational complexity by T of n, then it's A times T of n over B. So the recursive formula is that for small problems of size n larger than n0, the resource consumption is theta of 1, which means constant, else it's d of n for dividing, a times t of n over b for conquering, and c of n for combining. Now let's have an example. This was a practice midterm from 2016. That was, I believe, the first year that I taught the course, so there was no midterm at that time, no previous midterm, and I wanted students to be able to study, to practice. Suppose that merge sort runs in 64 n log n steps, and insert sort takes 8n squared. So we're saying that the merge sort is n log n. It's faster than the n square complexity of insertion sort, but the constant is worse, it's 64. So the first part of the question was, for which value of n does merge sort start beating insertion sort? So the solution here was as follows. What does it mean merge sort starts beating? We want 64 times n times log base 2 of n to be less than or equal to 8n squared. In other words, let's divide by n and let's divide by 8. We want 8 times log base 2 of n to be less than or equal to n. Now there are different ways how to solve this. You could use if this was a 2020 test, and this semester computers are allowed as long as you're not communicating with other students and, well, other people in general. We talked about that. You could run it on a computer. You could run it by hand. So let's take a guess. N equals 16. 8 times log base 2 of 16 is, so log of 16 is 4. 4 times 8 is 32. But n, which is equal to 16, is less than 32. And we want 32 to be smaller. So let's try a larger n. N equals 32. Or you know what, let's go for 64. 8 times log base 2 of 64. Well, log base 2 of 64 is 6. 8 times 6 is 48. And 48 is less than 64. Okay, we're getting there. So 16 is too small, 64 is too big. What about maybe 32? So n equals 32. 8 times log base 2 of 32, log instead of lg. Log of 32 is 5. 5 times 8 is 40. 40 is greater than 32. So we're somewhere between 40 and 60. You know, 40 is somewhat more than 32. 48 is quite a bit less than 48. Let's guess upper 40s. And again, in a 2020 test, you can run it on a computer. So that's the first part of the test. And the second part of the test is, how do we modify the merge sort to obtain faster performance on smaller inputs? Discuss the modification runtime, and there are many ways to do this. And I've said before that my style of tests, and the TA Vaibhav will likely confirm this for you guys, instead of inserting numbers into an equation and having 10, 20 occasions that you need to learn by heart, and that's it, I'm trying to ask more creative things. So how do you obtain faster performance on small inputs? So we know that for small inputs, the insert sort is faster. So let's use insert sort for smaller problems. So let's say that for problems of size less than upper 40s, insert sort is better. Let's just take an example. Suppose that you'll run insert sort for n up to 16, okay? So, and now let's take, if n is 16, choose insert, and then 16 square times 8, 16 squared is 256. Or another way to think about it, 16 squared is 2 divided by 4 squared times 2 to the power of 3. So 2 to the power of 4 squared is 2 to the power of 8. 2 to the power of 8 times 2 to the power of 3 is 2 to the power of 11. 2 to the power of 10 is around 1,000, so this is around 2,000. Actually, it's equal to 2,048. Now what about if we took n equals 13? So we run the insert twice, and it's an insert on size 16, and that takes 4,096, which is 2 times the 2,048, plus a merge. Suppose that a merge takes 10n, okay, just suppose, and n equals 38, this is 320. And now 320 plus 4,096 is something like 4,420, or, well, actually 4,416. And in contrast, without this basis case, we would have 64 times n times log base 2 of n. Recall, n is 32, log of n is 5. So this is 64 times 32 times 5. 64 times 32 is 2 to the power of, 64 is 2 to the power of 6. 32 is 2 to the power of 5, so 2 to the power of 6 plus 5 times 5. 2 to the 11 is approximately 2k times 5, which is equal to 10,000. 10,000 is worse than 4,400. We're coming out ahead. So that'll be it. This concludes this module. We'll continue next time.